Cool. Thanks, Peter. So hey everyone. As Peter mentioned, today I'll be presenting a paper that was released by Facebook AI Research a few months ago called ImageBind, one embedding space to bind them all. And really the why I chose this paper is because I really like that actually it's quite like a powerful thing that they're able to do, which is combining 6 different modalities into one embedding space and being able to do really cool like operations with these embeddings. But it's actually quite like a simple and accessible paper, I thought. Like they're not doing anything like really, I don't want to say like not groundbreaking, but they are applying existing methods and like combining them in this kind of new way to and show this kind of cool emergent behavior. So I thought that was really cool. And they give loads of examples, which helps you visualize like what's going on, which I thought was also nice. Cool. So without further ado, what is ImageBind? So ImageBind is an approach, as they say, to create one embedding space that joins 6 different modalities. So those modalities are images, text, audio, depth, thermal, and IMU data. What they show, or what I think is the kind of like contribution or the main contribution of this paper, is that they learned this joint embedding space even without having access to pairs, to each like combination of pairs of like modalities. So for example, they don't have like text to thermal like pairs. What they do is they have they have pairs from all other modalities to images, hence why it's called ImageBind, because they find that by doing contrastive learning with all modalities to images, you actually get emergent properties between other modalities, even though the models have never actually seen pairs of examples from those modalities. So I'll go into like a little bit more detail on that. But I guess the consequence of that is that they show that there's like emergent zero-shot recognition. They show like really good performance on zero-shot recognition tasks across different modalities, sometimes even outperforming like specialist supervised trained models that have been trained on those pair of modalities. So that's really cool. So they show that it's able to like learn and generalize across like unseen modalities, even though it's only been trained on like image to other pairs. So yeah, I guess the background to it is there's in the past, the work that's been done has focused on combining 2 sets of modalities. So like a really famous one is, and they mention it, is this thing called CLIP, which is by OpenAI. I'll share a little bit what this is, because I think it's a nice background on like what kind of work has been done on this in the past. So CLIP was released by OpenAI. I forget when, I think it was a couple of years ago, where they combine, they apply contrastive learning to images and text. What they do is they have a set of images and associated text. They have encoders for those images, and they train on the task of like basically bringing closer together positive pairs of images and text. So for example, this dog with the text Pepper the Aussie pup would be like brought closer together in the embedding space, and then all negative examples would be like pushed further out. And then this model, what it allows you to do then is do things like do like zero-shot prediction on like things like ImageNet. So for example, let's take all of the classes that exist, for example, in ImageNet or other image object detection data sets, insert them into like a prompt, like a photo of a plane, car, dog, bird, etc., which gives you an embedding, a text embedding for each of the classes. And then you apply the image encoder to this image of a dog. And then you'd have the highest probability would be a photo of a dog. So you can start to do these like classification tasks without explicitly having like a supervised model trained on this task. So this is some of the background research that's been done in this kind of space. But going back to ImageBind, I think one of the, I guess what they're doing here is they're creating, as they say, a single shared representation space by leveraging multiple types of image paired data. And how they do that is they align each modality to images, which leads to emergent behaviors across all modalities. Yeah, so this kind of the central part is this like image, the like image pairs. So I guess to jump into it, I might go through the paper a little bit quickly, but actually it's because I think I want to have a bit more of a discussion about it, because I think conceptually like it's a simple paper, but I think it would be cool to have a discussion about like what kind of stuff does this enable, you know, if you start to have like a shared embedding space across different modalities. So so they show here a little bit like an overview of ImageBind. So they have these different data sets, right? And the data sets enable linking images to some other modality. So for example, web image text is a data set which has images and captions. So that naturally lends itself to bringing image and text together. You have depth sensor data where you can have like the images and the associated depth sensor. Videos sort of lend themselves naturally to having like, you have a video and you have audio, right? So you can extract them separately, but like that is a natural pairing of like this video and this audio should be a positive example in the data set. Thermal data again with like the images and the associated thermal data, and then like the egocentric videos, which is like the IMU. So this kind of diagram on the right shows how they pair all of these different modalities ultimately to images. So once you have, yeah, as they say, so given an image I, and the like corresponding pair in this other modality, effectively what they do is they have these deep networks where they create these normalized embeddings for both of the modalities. And then they apply contrastive learning, which is kind of the technique I explained from CLIP, where the goal is to bring closer together examples that are positive. So the video and the associated audio from that video would be brought closer together in space. And then all of the other pairs of data points would be pushed further apart. And the idea being here that we're like learning, we're basically like learning which concepts of different modalities should be closer together in this joint embedding space. So you'd have like a lion, and the sound of like the roar of a lion should be close together because they're related to the same concept, or like, but a lion and like the sound of clapping might be further apart, right? So what actually happens, so it's always image to this other modality, but what actually happens is that as you train, as you use this method of contrastive learning, you actually get emergent behavior in pairs of modalities that the model's never seen. So what they show later in the experiment is that they can do zero-shot text to audio classification without the model ever actually having seen an example of like audio and text in the contrastive learning process. So they give some details as to the like implementation in terms of how they map, how they encode the different modalities. long story short, they basically use a vision transformer for every single modality. They sort of manipulate the data in order to fit the vision transformer model. So I thought this was really cool because like they, as I said, they don't really like, they don't actually show, sorry, they don't contribute like any new models specifically. Like they're using vision transformers, which I think, if I recall correctly, have been around for a few years. But yeah, the sort of contribution of this paper is is actually the method around it. So yeah, they use vision transformers. So each modality has its own vision transformer that is trained to generate embeddings for that modality. And then they apply the contrastive learning. Cool. So that's the method, really. Like, it's conceptually quite simple. You have like 6 vision transformers applied to different modalities, and then you use the info and CE loss to do contrastive learning on the pairs of data that have been obtained from these different data sets, bring them closer together, and push the other ones further apart. Any questions before I get to experiments?
Do they do like cross-modality contrastive learning? So maybe an image and audio pair, and then they're saying the negative pair would be that same image and a depth image pair?
No, I think they only do learning within image and another modality. So I think they consider, I think actually, yeah. So I think they basically like consider within, they take pairs of like image and another modality. No, I think you might be right actually, and then they basically negate all of the combinations of those pairs that don't exist. So in practice, it could be like you have an image audio pair and an image depth pair, but then they might say this first image and that second depth might be like a negative example, potentially.
Gerard, didn't
Yes,
you? Oh, sorry. Go ahead, Damien.
I was just very curious about whether they mentioned why they chose images as the like central modality for it all.
Yeah.
Not something like text.
So I think images, because actually images are the most commonly found thing that you can pair all these different modalities to. So I think they do mention it somewhere. So ImageBind here leverages web scale paired data, combines it with naturally occurring paired data, such as video, audio, image depth, to learn a single joint embedding space. So I think it's just naturally you have like these co-occurrences of modalities, which that's why image lends itself well to being the central one. I'm trying to think how you find text and depth, but that's kind of a text and thermal imaging. Cool. Sorry, Vahan, did you have a question as well?
Yeah, I just wanted to clarify. Didn't you say at the beginning that there is no binding between different modalities, or is it only binding each modality to an image, but not between each other?
So it's during the contrastive learning step, it's only ever seeing positive pairs of image and one other modality. So it's never explicitly told like this audio and this text should be close together in space, but it naturally learns that because it knows that those might be associated with like a similar image.
Okay, that makes sense. Yeah.
Yeah. The diagram in figure 2 is useful. Yeah. exactly. This one.
Damien, just unmute yourself if you have a question.
Oh, sure. Yeah, I was just kind of wondering whether if the image is like the linking entity between two examples of different modalities. I wonder if there's like if you had two examples of, let's say, one text and one depth, to be able to use this method to generate an image that creates a representation that links the two together. So it's almost like a, I don't know if they mention that anywhere in the thing, because we could potentially have a completely new way of visualizing like associations between concepts.
Yeah.
The thing is that this is just a representation learning paper, in the sense that the output of these models is you get the modality in and it outputs like a vector. But then if you wanted to use it for generation, for example, you'd have to train another model to do generation. So it's
Yeah.
so as it is, you couldn't use it for that.
So they show actually that like they have an experiment at the end where they will take these embeddings and replace it in place of the embeddings of like other generative models, and then you can switch the input modality. So let's say you have a text to image model, you could switch the text input to be an audio input, and now suddenly you have an audio to image generator, which is quite neat. They have an example. They have an experiment with DALL-E where they show that.
How do they take, like, for example, text is a sequence, or an image is a matrix? How do they take these and come, like, I guess they go through a VIT, so that means that no matter what, the output is a sequence. But how do they take that sequence of embedding vectors and make it into a single vector?
They apply a linear projection on top, I think. Where did they say this? Oh yeah, here. We add a modality-specific linear projection head on each encoder to obtain a fixed-size d-dimensional embedding that's normalized.
But that still would a linear projection would take each vector in the sequence and make it into a different size vector. But how do they? Maybe they take the last element in the sequence or something. I don't know.
So what do they say? So the resulting sequence, no, it's different. Yeah, I'm not sure. Does the transformer not output just one?
No, it's whatever size in sequence you get is the same sequence size you get out. So
Right.
yeah.
But I suppose could you then like apply a transformation to get like one vector from that sequence?
Well, usually what they do, based on what I've seen for like state-of-the-art sentence embeddings, is they just take the last element in the sequence of the transformer.
Okay.
But they train it when, like, for example, if they were doing that for this training, what they would do is that each time they would input the modality, get the sequence out, just take the last one and use that as the vector. And so it's literally trained to put all of the information into that last vector.
Oh, okay. I see. Yeah. I don't know if they have anything in the appendix. I don't think they do. But they do have something they do an ablation study, and they compared this projection head. So this is what I think is the linear layer. So they said they tried varying the projection head from a linear layer to an MLP, and showed the linear projection performs better. So I'm not entirely sure. I assume that means that they take the sequence and then transform it to like a vector. Yeah, sure. So yeah, they do quite a few like experiments to kind of show some of the emergent like capabilities. I found these are kind of like hard to see sometimes. So so yeah, so these are like basically using text prompts. They try to do zero-shot like classification tasks. So this is like ImageNet, for example. So they show that they can achieve 77.7 accuracy on ImageNet without like having trained on that. But it's obviously seen like images and text pair data. But I guess what they show is like even in these examples highlighted in blue, a very faded blue, they show that they achieve, clearly it's learning something because it's significantly better than random, to use text prompts to classify things around like depth or audio. And they also show like in terms of retrieval performance as well. So I think yeah, so this data set has like a text to audio and video retrieval. And what they show is that they get comparable like performance, especially for like audio and video, to like some of these other methods. So they show like it can do zero-shot classification tasks and also zero-shot text-based retrieval, which are comparable, which are like not state of the art, but I think like comparable to other methods that are not zero-shot. They extend this to do some like few-shot classification, which is quite interesting. So they have this like I forgot what exactly this data set is. They have so many data sets that they use that I get confused what the tasks of each one is. This is some kind of audio classification task, and they have like this audio MAE is like a self-supervised method, and this is like a specifically supervised method on this like audio classification task, and they show that it has like this few shot behavior where after seeing 4 shots of the class, like it can basically match the performance of a supervised model, and it's better than the supervised model at like lower examples.
I was wondering how do they like the few shot means that you feed in like 3 examples and then you feed in the example that you want to classify, but
yeah.
like how do they feed in the first couple and then that other one with these because each encoder like it just encodes that modality, but like if it's an image encoder and how can you feed in 4 images if it's trained to encode 1? Or like do they have something on top of this that's doing Oh, it says we train linear classifiers on fixed features for the greater than 1 case. Maybe that's it. They do additional training.
Yeah. Oh, yeah. 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 Good question though. So the first set of experiments is showing basically this kind of zero-shot, few-shot classification emergent behavior. This is my favorite. My favorite part is coming up now, which is like now that you have this like embedding space which has multiple modalities, what does it mean to do like arithmetic what does it mean to add like a vector for an image and a vector for audio? What do you get? Which is quite cool. So in this figure, they show they do image retrieval. So they add the vectors for like this image of fruit and like chirping birds, and these are the closest images associated to that vector. So you can start to see it's like mixing the concepts of like the fruit and the audio to get similar ones. Similarly with like a photo of what looks to be a bride and clapping, and so you get like different wedding photos, and a clock and church bells, and you start getting clocks of like different churches. So clearly it's like learning some kind of concepts of like what these things are, which I think is like pretty good evidence that like there's something like there's clearly learning something, right? There's learning concepts. This one kind of blew my mind a little bit. So here, what they do is they do object detection, but instead of doing it with like text-based queries, they do it with like audio-based queries. So remember the image I showed you in the clip paper? Actually, let me go back to it so you can see. So in this clip paper, they show this like zero-shot prediction, where what you do is, let's say you have this image of a dog and you want to classify this image, and you have a set of labels, so plane, car, dog, bird. What you can do is you can embed this prompt, like a photo of a plane, car, dog, etc. And then you can basically find which pair of these text of different classes with the image has the highest probability. So that's what they do in clip. But now what they've shown is like, imagine instead of having text, you have audio signals. You have the audio of a dog barking. You have the audio of like a keyboard typing, or of a clock like ringing bells, and you pass them through and you have an image. They show that you can do like object detection based on audio rather than like text. So what that ends up with is you have these objects, and it's basically associated like this image with like the audio of a dog barking, or like this image of a keyboard with like the audio of a keyboard typing, etc. So that's like two examples of things they do. They show in the first figure in the whole paper, they show some other kind of cool examples. Most obvious one being like cross-modal retrieval, right? So if you have the audio of a fire, you can extract images from it, you can extract depth, you can extract text, you can use like an image to extract a sound, different things like that. You can combine them to do retrieval across different modalities. Embedding space arithmetic is kind of what we just saw. But then, yeah, they show this like audio to image generation, which links to what we were talking about before, Damien. So what they did in here is that they take a pre-trained DALL-E 2 model, and they basically sub out the text embeddings and feed in audio embeddings. So now you have like the audio of a dog, and then it generates this image of a dog, and the audio of fire and rain, etc. So it generates these images based off just a sample of audio.
This could also be like really cool, maybe to help deaf people understand the world or something like that. So for example, if it starts raining outside, maybe they'll have like a microphone that takes that, and then we'll put an image on their computer just showing rain. So they're like, oh, it's raining outside, even though they can't hear it.
Yeah.
That'd be cool.
Yeah, totally. You can like transcribe things. Yeah.
Same for blind people.
Yeah, true.
Yeah.
So cool. Such a cool paper.
Yeah, so the last steps of the paper really is, oh, sorry, it's not, for some reason I can't zoom out now. It's great. Cool. Okay, I can't zoom out anymore. So they do, the last step of this is really just like, they do a couple of different experiments where they show how varying different experimental setup impacts the results. I think the most interesting result that they find here is that scaling the image encoder leads to better results across different zero-shot classification tasks, which is super interesting and kind of makes sense when you consider that the image is the underlying like core of this whole method. So they show here that they scale the vision transformer. They have these different, I don't know what the letters stand for, but they have these different size vision transformers. And they show that the performance increases, sometimes quite significantly, as you increase the capacity of this model. Trying to think if there's anything else. Yeah, data augmentation, I thought this was interesting. So they found that sometimes, like, if you apply too much augmentation or too strong augmentation to images, it can have a bad impact on some other modalities, but not others. So interestingly, like strong augmentation helps image depth, but it like decreases the quality of like the audio setup. So there's some like interesting things that you could vary, depending on what you're looking for from the model. Yeah. I think the last thing I want to highlight, which I thought was interesting, was they tried using. So what they did, the last thing they tried to do is use this method that they call ImageBind as a way to evaluate models. So they take they switch out the vision transformer for images and replace it in with these two models, Dino and DIT. Now, this model has a higher, a better performance on ImageNet. However, when applied to this method of ImageBind, it performs worse on, well, definitely on audio. On depth, it sort of matches, but on audio, it performs significantly worse than this other model. So then the question is, what does that tell you about that model? Like, what does that tell you about the base image model, given that we know that larger vision transformers tend to lead to better zero-shot performance across different modalities? What is that sort of gives you an evaluation tool to say like, yeah, what does it tell you about like the model that you've trained, even though it's better on a supervised like image classification task? Cool. Oh, I can zoom out now. So that's the paper. I'll kind of stop there.
Do they make the models in code open source, or at least are the data sets they used open source? Do we know?
I believe the data sets are. I know. I actually think they made everything open source.
Okay, sick.
Yeah, I'll post the GitHub repo on here in case people are interested. So actually, where I first came across this paper was I was at a meetup for Weaviate, which is a vector database, and there was someone presenting this paper, but obviously with like the thinking of now that if you have these like different modalities in a one embedding space and you apply a vector database on top of that, you can do retrieval, like it's like really cool retrieval things across different modalities. So that's the context in which I saw it, and he had like put together a demo. So yeah, assume it's all like open source. So yeah, I guess like I'm curious to hear, does anyone have like, as you're going through the paper, did anyone get any ideas for like things you could do, like now that you have a joint embedding space for different modalities? We already had a few ideas like for aiding blind and like deaf people, you can translate things to different modalities, but any other ideas that came to mind?
So one that sprung out to me immediately, not necessarily as a application, but like a depth sensor and a camera and an IMU are like really common on like automated cars. And then they usually have like LiDAR as well, but that's depth sensing, so it's just a more expensive version. So I was wondering if I was thinking this seems like something that might be used in that context in some way or another, maybe to like create more robust representations of the world. The other thing I was thinking, and we've seen this in other papers, is that I've seen people write in other papers how the way that humans tend to understand things is that they have multiple ways of understanding it. And like a lot of that comes from understanding it through different modalities. So, or world models. Anyway, so both of those things make me think that there's a place for this in terms of robotics and automated driving as like a form of robotics, because yeah, it might allow for like a better semantic understanding of the environment. Not a very concrete application.
Maybe like weather prediction, combine images with temperature and output text.
Yeah, actually related to that, I was thinking, if you have different, let's say weather forecasting is a good one because you naturally have data that is belongs to different modalities. Like could you create like a model that can leverage all of these different modalities to do like some kind of final downstream like prediction task? What like implications does that have for sort of downstream tasks where you might naturally have different kinds of data available to you?
Peter, I don't know, like, could you see this being used in robotics? Because a lot of the time, I feel like in robotics, like having access to multiple modalities of inputs might be useful.
Yeah, for sure. I'm trying to come up with like a more probably like the most specific application I could think of in robotics would literally be building like an internal model of the world, taking into account multiple modalities. That could make a lot of sense for me in terms of how you would use this. Maybe within the latent space or like within the embedding spaces where you keep track of that. There's a lot of interesting things that come from different, like the information you get from different modalities. Like, for example, touch is a modality that can provide a lot of information about like local detail, but not a lot of global information, whereas images can provide a lot of global information. I don't know. Definitely feel like there could be applications. Also, one of the biggest problems that exists in general with robotics is that it's not robust to changes in the environment. And I'm wondering if there's a way that you could leverage how varied the data is here to come up with like a way that the model could be automatically more robust to changes in the environment.
I was wondering as well, imagine if you had like well, this got me thinking because I don't know if you've seen like Spotify are releasing like AI translations for different podcasts. But if you had like an ImageBind, which is trained on like video and audio in one language, and then like video audios in different language, could you then like have the same video, but then like translate it to like generate audio from like in a different language?
Very
So like
super
map,
cool.
yeah.
You realize this is becoming an all-knowing, all-seeing robot. Just a nice embedding space.
Yeah, but like right now it can only perform classification. There's a lot of limitations to this. Like, and also you have to question how much information can be encoded in like a d-dimensional vector, you know? Because at the end of the day, that's what's being outputted by these models, and that encodes all the information about whatever the modality contains.
Yeah, I was thinking exactly the same, because if you want a video or a song, you may have to increase the embedding size. There is so much information there, right?
So I think the power really comes because these so cross-modal retrieval and embedding space arithmetic, these embedding space arithmetic is actually also just a retrieval task. Like they just add these two vectors and find the nearest vectors to those. But I think this application, audio to image, to me was like the coolest one because you're effectively combining this learned embedding space with an already pre-trained model that's trained for like a specific task. So you can imagine like you could have all these models that do different tasks, and suddenly you feed them in with this like representation of the world with different modalities, and like you can start getting these weird, funky behaviors or applications.
Yeah, I was thinking an interesting, like again, I think I'm thinking too abstract for answering your question well, but like just taking sequences of these types of embeddings and trying to do something with that. So like audio of a fire plus a depth sensor, depth image of a like a fireplace, maybe plus like, I don't know, an image of a forest, and see what comes out of it, and or try, seeing what can happen with sequences as opposed to just doing the arithmetic. Anyway.
Yeah.
Like echolocation could be an interesting one, because you could combine image with audio and then potentially output depth information. So I wonder if like you could,
Yeah, that one would be really cool.
3D map out a room based purely on an image and some like internal.
Wait, so then that's so cool because then that applies to like autonomous cars as well, right? Because LiDAR is really expensive, right?
Yeah, at least right now. I'm not sure. I think it will stay expensive, but I'm not sure. That's why, like, I think Teslas don't even have a LiDAR on them, and they're not going to put one on because they don't view it as like a viable way to develop autonomous driving, to have a LiDAR on the car and still have an affordable car.
Yeah, Lewis, I think like I like your idea with publishing as well. There's probably so many like existing things that like could be done, or like things that it opens up in the world of search. Search feels like the biggest sort of enhancer or gainer from this paper.
Yeah, and it would be a really, I mean, we have this problem. So we do have metadata generally with the images, but that may not necessarily be the case. So yeah, it would be interesting, and we do have like images that relate to articles, obviously. So yeah, it'd be interesting.
Literally at this meetup for WeP8, it was just like they were so excited because it's like this paper just makes them so relevant, like vector databases. So obviously lapping it up.
I wonder if like a corollary to all of this stuff happening in ML is that we start wearing more sensors, or our sensors on our phone, for example, are on more often, or something like that. Or we start installing them in everywhere so that we just have like massive data collection all the time.
I think Meta released their sort of wearable. I don't know. I heard something about it, but yeah, probably depends who owns the data, though. I guess whether they're just using us to mine, whether we own that data or they do. I guess.
Yeah. Another interesting like thing that could happen off of all of this, or it probably should happen, is like we start having some kind of ownership over our personal data.
Like in stocks trading or like data trading.
I mean, it's already kind of happened with the Hollywood strikes, because the whole idea was that they were gonna companies were gonna film you once and then use the film to generate like extras in video in movies. So they basically were gonna own your image / person, I don't know even to call it, maybe avatar, forever. And they're like, we're not allowing this to happen. That's a pretty good example of like ownership of your personal data, where your personal data is actually literally just your body and you.
That was like the first Black Mirror episode this new season, wasn't it? Cool. Thanks everyone. I guess, is there any other comments or questions about the paper? If not, then thanks everyone for attending this week's paper club.
Thanks, Gerard. This was a really cool paper and a cool discussion.
Thanks,
Yeah.
Gerard.
Thanks.
See everyone.